So you just, great. Thanks, Jason, for the introduction, and good morning, everyone. Before starting, I wanted to thank both TMOS and Fleet for organizing this joint event, this joint seminar. During the next 40 to 45 minutes, I would like to take you on a journey regarding our learning and development over the last several years of this novel platform for epitaxial graphene on silicon wafers. So let's get started. Of course, before getting into the details of it, I would like to make quite a few acknowledgements. I won't go through all of them, but clearly I would like, first of all, to thank the current members of my lab, the Integrated Nanosystems Lab, and as well as the various alumni, and actually I see some of them here, which is great. The many collaborators throughout the years that have been extremely important, and you will recognize quite a few familiar names through the whole list. And as well as, of course, the funding sources and agencies that have been supporting us over the years, which is clearly from the Australian Research Council, first my future fellowship, and then the ARC Centre of Excellence, as well as the DST group here in Australia, the Department of Defense in the US, and the various like Australian Synchrotron, ANSTO, ANFF, that have really been very important to getting access for specific fabrication and analytical capabilities. So said that, so this is more or less my outline. It might a little bit change as we go, but initially I would have to go through what is this platform? What is this epitaxial graphene on silicon carbide on silicon? What does it do? How we came to that? Why we were motivated to work on this at all? And some initial basic properties. After that, I would really like to dedicate some part of this time to, I will probably pick a few of these application areas. So the application areas that we are really focusing at the moment are more or less these four. So integrated optics, nanophotonics, like metasurfaces in mid-infrared, I will talk to you about that for sure. Energy, we will be focusing on energy storage, integrated energy storage, particularly supercaps. I might not say too much about that though. Biosensing, particularly in terms of brain sensors. And this is a very fascinating area that we started relatively recently and is extremely promising. Leading towards brain-machine interfaces. So I'll say something about that towards the end of the talk. And the other area, which is we are still in the early phase of characterization, but we're working on this as well, is clearly terahertz properties of this material and its potential metasurfaces and application. And then, of course, I will end with summary and perspectives. Before getting to the detail of the work, I need to go through basically a few preambles here. So first of all, what is our take? A lot of people work on graphene, but our take is slightly different, I'd say. And our take is really focused on how can we integrate the properties of graphene into a silicon platform. Why is that? Because it turns out that particularly when we talk about miniaturized applications, it is extremely important to make sure not only that the graphene is the right graphene for the right application, but also that the graphene is integratable into the current type of manufacturing in semiconductor industry. And this is a little bit of a weak point for graphene in general that we will talk about at length. But clearly, graphene, as much as all of the new 2D materials, there's many since graphene was first pointed out. They came to exist and were discovered. All of them, of course, can potentially offer capabilities that were not available before that in the normal, more conventional thin layers that we are used to work with in semiconductor industry. And typically what's going to happen is that these materials, because they are 2D materials, are not only extremely thin, but also very weakly interacting with any other a layer around chemically, although there's quite there's a few points that I will make about that. Anyway, they behave in a very, very different way. And they're made of surface. Surface generally is a part in the semiconductor industry that has always been dreaded. The more surface, the more potential problems. And clearly here we reverse the equation. We want to use the surface. So there's a lot of challenges there. However, there's a lot of promises because a lot of unprecedented potential capabilities. And the fact that clearly with a 2D material, you can achieve the ultimate miniaturization that we're really after. And not only the ultimate miniaturization of electronics, but the ultimate combined miniaturization of electronics, photonics, and a lot of other things, which is really the holy grail going forward for miniaturized technologies. Now, a couple of preambles, starting from this one. Right now, of course, graphene is considered already like an old 2D material. Since then, there's been so many additional 2D materials that have been discovered, studied, and very, very different properties that we start understanding right now. And for a while, people thought, okay, we probably know everything that we need to know about graphene. We know the whole theory, how the ideal graphene behaves, exactly what we can get out of this. And so there's nothing else to be discovered anymore. I kind of disagree with that point of view because it's not necessarily the full reality. Just as an example, not long ago, this new part of science has been kind of started, what we call now Plasmonics. And it started from the shifting, basically the rotation of layers of graphene. This is particularly promising. From anything that is electrochemical applications of graphene, there's still a lot to be understood. And it's also very complex, and there's a lot of different variables that one has to understand. Hence, this quite provocative paper that came out last year about, is that true that anything you put into graphene will improve its properties? Well, probably not. It's just that we are still after a more comprehensive understanding of what is happening with graphene. So that's the first preamble. There's still a lot to be understood. Second, it's the nomenclature that we use. So I bet that, well, probably to physicists, if you ask a physicist what graphene is, well, they might more or less align into the same type of definition. But if you start asking a chemist what graphene is and a physicist what graphene is, I bet that most probably those two answers will differ. And in material science, of course, we're working across a lot of different disciplines. So this misunderstanding will amplify more and more. And this means that when we think we're talking about the same thing by talking about graphene, many people will have different understandings, and this will create confusion. And the other thing that creates confusion is the fact that being a 2D material, of course, it doesn't behave like a normal thin film that people were used to work with. This also means that a lot of what we call the properties of the ideal graphene are really properties that are based on an infinite sheet of graphene, which is almost an entire, no grain boundaries at all, perfect graphene, suspended in vacuum and such, which is what I call the ideal graphene. But in reality, most probably, this is not the graphene that one is going to use for actual applications. So all of this contributes to a lot of confusion. And I think in recent times, maybe things have been converging again, but this is something that people have to definitely be aware of when talking about graphene. So that's the second point I wanted to make. The third point is integration, and particularly integration in semiconductor industry, which is what I'm referring to, has been particularly challenging for this type of material. And it will be not just for graphene, but also for the other 2D materials, because exactly they are 2D materials. And the way the community has worked most of the time in terms of understanding how graphene behaves has been by using flakes, exfoliated flakes in many different ways. Now, clearly, it's what we're talking about here in terms of integration in semiconductor industry. We're really focusing on to wafer level growth and wafer level integration. And this means that even though you might be able, and this has been demonstrated, by the way, I believe by IBM, to make a big flake of graphene, synthesize a big flake and transfer it completely to cover the whole wafer, it does not mean yet that you will be able to integrate that. There's a lot of problems that can come out still. That's wrinkling, delamination. Delamination is going to be a very important factor because being a 2D material is only the layer is only held together by van der Waals forces to its substrate. And clearly you can understand van der Waals forces are strong, but they're also pretty weak in terms of semiconductor processing. So the lamination is something that happens very easily through the many, and I'm talking about hundreds of wafer level steps that need to happen before having the final product, maybe an integrated circuit of any type. I also remember that remind that the CT of graphene is negative. So unlike most of the conventional thin films, this means that any load of thermal loads or mechanical loads which happen at the wafer level, CMPs and such, will probably lead to some type of failure. So basically, in terms of integratability of the material, what one has to be taken into account is the fact that certainly these factors like manufacturability, reproducibility, yield, predictability, reliability are often more important than the final absolute quality, as long as the absolute quality, of course, performs how you want to, and the predictability is there. So basically, what this is a long-winded way to say, often when you do some practical work in industry, you will have to find the sweet spot that allows you to attain the performance you're looking after, but also integrate the material into a final product. So these are the preambles that I needed to make before getting into the specifics of our platform. And it justifies why we were really looking into wafer scale level growth, and particularly on silicon. Why is that? Well, actually, you are certainly familiar with epitaxial graphene on silicon carbide wafers, so I won't get into the details of that. This is as old as the graphene by Scotch tape, so a lot of progress has been done during the many years. You can see here graphene on silicon carbide wafers, and you can see that they are carbide because they are transparent here in the visible. So a lot has been learned about that. So this is the wafer scale growth that I'm talking about. And why does that happen on silicon carbide? Is because carbide can act as a solid state source of carbon, and particularly as a template. So what usually happens very quickly is just that we use what is called thermal decomposition. So at very high temperatures, meaning 1500 and upwards, in ultra high vacuum, we're basically playing around with the different vapor pressures of the silicon species and the carbon species. The silicon species will tend to leave the surface much faster, leaving an excess of carbon on top of the silicon carbon template that will reconstruct itself as a graphene in very easy words. And I won't talk about the buffer, and I'm sure you all know about these things, but I just wanted to say, of course, wafer level graphene has been studied a lot onto silicon carbide wafers. This is, however, not what we focused on. We really wanted this on silicon. Now, it turns out that you can grow silicon carbide on silicon, and you might try to repeat the same trick with thermal decomposition so that you have in the end graphene on silicon carbide on silicon, right? It turns out, though, that repeating that trick with the system is particularly challenging. And it always ends up with high defective graphene and not necessarily uniform. Why is that? Well, actually, there's quite a few reasons why this is the case, and quite compelling reasons. First of all, if you have a look at the template that we're working with in this case, which is silicon carbide and silicon, because of the lattice mismatch of these two materials, it is particularly challenging, extremely effective. And clearly, if you start with a defective template, you will have a defective layer. That's quite straightforward to understand. Temperature limit as well, 1440 silicon melts. You cannot go much higher than that. Well, actually, you cannot go much closer to that. That's what I really meant. Otherwise, you will have certain problems. So that the temperature limitation is another big problem. However, the push to get to that is the fact that not only if you had the capability of obtaining graphene or silicon carbide on silicon, not only you would have the silicon platform to work with that is much easier, much more integratable with the rest of the silicon technologies, but you could also play with the selective growth that I'm going to show in a minute, as well as taking maximum advantage of the easiness of actually constructing these nanostructures made of this combination. So silicon carbide structures coated by graphene. And there's quite a lot of areas where this specific combination is of interest. So not just the graphene by itself, but the combination of silicon carbide and graphene. And nanophotonics is definitely one of them. And so metasurfaces and such, and I will show you that a little bit later. So the thermal decomposition does not work. So basically, what can we do? We still want to have that platform working for us. What else can we do? This is how we came to this different approach of using catalysts. Of course, usually when you have a major problem, also in terms of temperature, catalysts help. And catalysts had been looked at before, for example, nickel on silicon carbide and silicon, but it didn't work particularly well. We thought instead of using a combination of catalysts, and particularly the choice of catalysts turned out to be extremely important. We came up with an alloy of copper and nickel. So by using copper and nickel as a layer of very thin layers on top of silicon carbide and silicon, what we are able to do is extract the carbon from the silicon carbide at relatively low temperature, and we are usually working around 1100. And well, compared to 1500 and 1700, clearly all is relative, but it's clearly much more palatable in terms of temperature. But not only that, so the nickel works very well to release the carbon at relatively low temperatures, and the copper really is able to obtain a very fast graphitization of the carbon that is released. And these two materials work really in synergy. And just to give you the idea of how this works is, for example, you have here a plot of ID over Ag. If we were using only a thin layer of nickel, you would see that we would be most of the times pretty high in terms of ID over Ag. But the combination of nickel and copper can get us pretty much down here, which is not perfect graphene. This corresponds, so this type of D band corresponds to probably around what we have estimated about 100 nanometer of grain size, but it's still good enough for some of the application that we want to look into. And so remember this 100 nanometer, because this will come back into some of the considerations regarding sheet resistance. So this is basically the approach that we started working with. And of course, initially we went through a lot of basic characterization using a lot of different approaches. The soft X-rays as at the synchrotron have been extremely helpful here. You can see it at the very top of the substrate. We have a thin EG, so epitaxial graphene layer. Underneath, we have the silicon carbide. And then we find some oxidation that has been confirmed as well by looking at the silicon peak in the same way. So we do have oxidation just up underneath the graphene that we form. And I just wanted to remind you that when we work at those 1100, which by the way, another thing I forgot to mention about that 1100, the reason is also that 1100 degrees that we use for the synthesis of graphene is a temperature where we're working, so the nickel and the silicides and the copper are basically in a melt. So we're actually working in liquid phase epitaxial growth. And this is the reason why we can get to such better coverage, more uniform coverage, and more consistent coverage, because we actually can relax a little bit the constraints for that from that very, very defective silicon carbide underneath. So that's an important thing. But we do work in medium vacuum conditions, so we do have some back pressure of oxygen, which shows up in this way. And this is an important thing, again, when we look into the transport properties of this platform. Now, I was explaining before, one of the appealing things of this approach is that by having the silicon carbide on silicon, and the silicon carbide is our source of carbon, we can play this trick very easily, which is pre-patterning the silicon carbide at the wafer level, so all over the wafer in the way we want, micro nano pattern. And by applying that graphitization that I just explained before, so the two metal layers, we don't have to structure that at all. We will have self-alignment of graphene on top of the silicon carbide, and not just on top, but actually conformally around. And this really simplifies the way we can work with the system, silicon carbide and epitaxial graphene. And this was one of our early examples where we showed that, for example, we could make these suspended bridges on silicon by pre-patterning the silicon carbide and then do some surface micro machining of the silicon, and then obtain the graphene directly on those silicon structures. So any type of structure, even 3D structures anywhere on the wafer, can be graphitized in the way that I explained. Also because we're working in liquid phase, so this really helps the conformal coverage of the catalyst for all around any type of structure of silicon carbide. So you can see here that this is really made of the TO and LO of silicon carbide and graphene. Anywhere else is only silicon. So this process is naturally selective. This is just quickly to show you that we can apply this also to very complex structures and these disordered structures, to be honest with you. So that these are silicon carbide nanowires that were grown by BLS onto silicon substrates. And we have been able to graphitize them by treating a little bit of process in the same way. And we also, so basically we obtained from silicon carbide nanowires, graphitized silicon carbide nanowires with a very thin oxide as an intermediate shell in between the graphene and the silicon carbide, in the same way as we worked with the actual flat surfaces. Now, adhesion, why did I want to mention that is because, as I said, for integration purposes. So most of the graphene that is transferred onto silicon dioxide or other surfaces tends to show, if you actually measure quantitatively the adhesion of the layers, tend to show quite a low number. And actually, these are pretty much the numbers that, with the practical adhesion calculated into it, correspond to van der Waals forces. In semiconductor terms, anything that is below 2 joules per meter square means potential failure. And I know very well that because I worked for a while with materials that had that type of problem, which were porous dielectrics. And basically, in the end, for many reasons, and adhesion was one of those, we could not go for ultra-porous low-K dielectrics integrated into our common ICs just because of the adhesion problem. It turns out that this type of the platform that I'm talking about, we managed to quantify the adhesion energy, and we are more around the 6 joules per meter square. Now, this is very favorable in terms of integrability because, of course, we have a much better number. It also shows you that, of course, it's not perfect graphene, right? Because the only thing that can enhance the adhesion is potential bonding, right? There's no, if it was just van der Waals forces, it means that, we would have gotten this type of numbers. And again, remember about that sweet spot. We do have grain boundaries, and most probably around those grain boundaries, there might be some oxidation bridges towards the substrate. However, those boundaries, in terms of sheet resistance, don't necessarily show up as a worse type of transport, not necessarily. But in terms of electrochemical applications, those boundaries are extremely important and extremely beneficial. And I hope I will have time enough to explain to you how. Okay, now let's come to the different applications that we are looking into. And as I said, I will focus a little bit more into the metasurfaces, the MIR, and potentially more on this side too. I don't think I will say much about energy storage, but before even getting to that, I would like to make a couple of points regarding the transport properties that we're able to assess. Also thanks to Fleet. And now we found here, when we were looking at transport of this type of graphene, as I said, small grain graphene compared to the micron size that you will get out of CVD graphene and such, and even from silicon carbide ingots would have microns and up in terms of grain sizes of graphene. Now, nevertheless, in terms of sheet resistance, we found something that is pretty much at the best, so close to the quantum values that we would expect to get from graphene. And particularly when you look at this graph, so you have here mobility and versus sheet carrier density. This is so. As I said, the difference between ideal and practical graphene. So every time you have supported graphene will behave like that. So there's a power relation in between mobility and sheet carrier density. And those things, of course, cannot be changed in any way one wants, but they are connected. So meaning that the higher the sheet carrier density, the lower the mobility and vice versa. So if you want to have high mobility, you will have to have very few carriers. That's how it works. You can only move on this line, along this line. Now, the thing that I wanted to draw your attention to is that if you look at these triangles here, these are triangles that were measured on epitaxial graphene on silicon carbide wafers on the silicon face, so on the hexagonal silicon face of carbide. These more rounded points here are actually the graphene that we have grown with our process that I just explained onto different, the 111 surface and 100 surface of silicon carbide on silicon, because they both work. They both work, but they work in a little bit of a different way. As you can see here, the graphene that we grow on the 100 surface tends to have a particularly high, really high sheet carrier density, as you can see here, and of course, very low mobility. Whereas the ones that are grown onto 111, they have a slightly lower sheet carrier density and a little bit higher mobility, and it starts basically crossing over with those points from the silicon carbide wafers. So what is really happening here? Here, basically, if you move along this line, they are all equivalent points in terms of sheet resistance of the material. So from that point of view, they're pretty much all in the same ballpark with a little bit of variation. But what is really determining here is the amount, is this relation. So how much carrier density do you have in your material, and what is causing that high sheet carrier density? And this is what we wanted to understand a little bit more. So I thought that this is what was really quite surprising, probably not that surprising in hindsight, but just considering that this material here has only about 100 nanometer grain size, and these other material here have microns sizes in terms of grain size. Nevertheless, in terms of resistance, sheet resistance are pretty much equivalent, right? Non-mobility, clearly, but sheet resistance. So this, we wanted to understand a little bit more. Why do we have such a high carrier density, and why it is higher? Why is that higher for the 100 surfaces? And so DFT helped us a lot here. Together we did that together with some of our collaborators in the US. And we had to take into account that oxidation that I explained before, that we found consistently any time that we did the surface characterization. So the oxidation has been taken into account into the cells, both for the 100 and the 111. And in the 101, from our surface measurements, we also found that actually we do have a buffer as much as the buffer that comes out. So this surface is pretty much corresponding to the 0001 surface of the bulk silicon carbide. We do have a buffer as well, but we do have the oxidation. Here on the 100, there is no buffer because of just the geometry of it. We have the oxidation, so the this oxidation layer that is basically exposed towards the graphene directly, and we have a high amount of charge transfer because of that. And indeed, our graphene is invariably p-type because of this high charge transfer. And this is why we found that with the 100, we are basically down here, very high sheet carrier density. These are actually numbers that we could confirm by DFT. And why do we have slightly lower charge transfer, positive charge transfer into graphene, in this case 111, is because we have a buffer layer. And that helped us basically to move this a little bit higher here. And this explains very well why we have this different behavior, and also explain very well how important, not that this wasn't known before, but how basically the interface structure in between the graphene and its substrate is so important when the graphene is integrated. In this case, basically in terms of sheet resistance, the composition and the structure of the interface clearly is dominating with respect to the size of the grain. So this is a very important thing for us to know. Okay, so I won't go through that because it would take me too much time. I did want to go through a little bit the applications now, particularly let's start with the mid-infrared metal surfaces. So basically here the idea is that now that we can make any complex structure at the wafer level composed of this silicon carbide coated by graphene, how can we use this in terms of, for example, IR detection? Very quick interlude about this is basically what we are doing as a contribution to the TMOS Center of Excellence, which is the new Center of Excellence just started early this year officially. So concentrating the meta-optics and meta-surfaces, and particularly geared at generating, manipulating, modulating, and detecting light in flat, very, very thin systems. So basically, there is a very strong interest in this field towards, for example, mid-infrared sources, not only sources, but also, systems that can work for mid-infrared detection. And there's different reasons for that. One is that chemically, there's quite a lot of fingerprints of interest exactly in that region that one could probe, and one could probe at a standoff distance, so without having to actually make contact with that, which is important for quite a few applications. Second thing is, for example, navigation and imaging at distance by, for example, time-of-flight systems. One is LiDAR, for example. And why mid-infrared? Well, infrared is clearly beneficial in terms of being able to see often through some level of fog or some level of smoke, as well as, well, not the whole infrared, but certainly the infrared tends to be retina safe, which is also another important thing that you wouldn't be able to do with visible laser. Just shoot a laser all around with people walking around would be a very big hazard. So there's quite a lot of interest into mid-infrared. And what can we do here with this platform? I will say just a few words because probably I'm heading towards the end. But basically, we are using a combination of the plasmonic response of the silicon carbide with the surface phonon of the surface phonon of silicon carbide and the plasmon of the graphene. Silicon carbide is a polar material, so it has a surface phonon response in what we call the Reststrahlen band, which is this band in between the TO and LO peaks of the silicon carbide. So it's about this region here, 800 to roughly 1,000 wave number. In this region, basically, the material behaves as instead of the dielectric, it behaves as a metal. And thanks to that, you can actually have a phonon response which is much more peaked and low loss than compared to most of plasmonic materials like silver, gold, and such. Drawback is that you are stuck with this very narrow window, which is in the infrared, but is not tunable. There's not much you can do about it. However, there's this very good potential benefit to be drawn out of that. So what can we do once we coat this silicon carbide with graphene? So we know that graphene has a plasmonic response. So if you look particularly here at this dispersion, this is a back of the envelope calculation. So the numbers are just a ballpark for you to have an idea. If you wanted to basically focus on the response of a silicon carbide, just the surface phonon, that's more or less the band that you're constrained with. But actually, when you start combining, because you can hybridize the plasmon and the phonon response, and once you do that, you actually can enlarge the responsivity window of your system. And not only you can enlarge it thanks to this graphene on top of silicon carbide, but you can tune it dynamically. Sorry, you can tune it dynamically by changing the charge concentration in situ of the graphene, which is one of the really one of the most important contribution that actually graphene can do is the dynamic tunability. So this is really very, very promising, and we started looking into that initially, particularly from simulation perspective. And this is basically what tells you here. If you, for example, consider it as nanowire, that one that I showed you before, nanowire of silicon carbide only would have a TO response depending on the orientation, and would have a localized surface phonon response that has to appear in between that window of TO and LO. Overall, though, you can see that the absorbance is very small. However, when you coat it with graphene, the surface phonon and the plasma will hybridize and split in two modes, as you can see here. So we will call here M1 and M2. And those two modes, as you can see, are appearing outside of the Westeralen. And this is really the important contribution of that hybridization, is that we are not longer conditioned by that narrow window. We can enlarge the window and then potentially also tune it around. Now, you remember that we had that additional oxide that I talked about, practically when we do our graphitization the way that we in our platform. And this introduces some interesting phenomena, because actually not only what you can see here already is that the absorbance overall is increasing. For example, look at this mode here. The absorbance is increased by having this oxide, but it gives also confinement. So actually what we have at this point in time is that, and this is just very quickly, this is just the silicon carbide bare nanowire, how it responds, and you can pay particular attention to the scale here that are different, right? When you look, for example, at M1, they were particularly interested in, you can see that the field is amplified and particularly confined within that low refractive index oxide that we have in between the outer shell of graphene and the inner core of the silicon carbide. So it turns out that that oxide acts as a coupling medium, and basically depending on whether you're getting to overcoupling or undercoupling, you will have to find your sweet spot. But doing the things right, you can get several tens of enhancement in terms of the field enhancement and the confinement you can get into that very thin oxide in between carbide and graphene. And this would get naturally, because I explained how the process goes, we do always get that very thin oxide in between. And it turns out that is actually very beneficial. So of course, what we would like now to do is have this approach of, we can basically design now that we have the full system already set up in our, we have a full model set up. We can start devising actual meta surfaces that can act do different things for us. It can filter out different properties of the light in mid-infrared. And this is really one of the major threads that we will follow up going forward in TMOS. And clearly what here we're aiming to is static tuning by just the structure itself. Of course, that's straightforward. And then dynamic tuning at the same time by gating the graphene and being able, given a certain design, to shift around the responsivity and of the system. I guess we are getting quite, yes, Jason has given me the signal, so 15 minutes to go. I will have to be quick. So I will jump completely this part of the electrochemical that I said already I wouldn't do anyway. But I did want to say a couple of words, and maybe, Jason, can you just suspend a little bit, just for a moment, the recording, please? And then I just quickly, thanks, Jason. So yes, I will just end here. I won't read through here through the whole list, but basically I wanted just to share with you some of the long learning that we had over the last few years about our graphene on silicon carbide and silicon. There's been a lot of challenges to be overcome, a lot of interesting learning, and a lot of very, very interesting perspectives as well. So thanks a lot for your attention, and I'll be really happy to answer questions.
I know Simonte had a question. If Simonte's there, do you want to just ask it, Simonte, directly?
Hi, Francesca. Thanks for a great talk. My question is that as you showed that the graphene can be grown around silicon carbide nanowires, so can this technique be used to make carbon nanotubes as well?
Francesca, did you get that?
I heard nanowires, but sorry.
Yeah, do you want to look in the chat? The question's in the chat, but she's asking, can silicon carbide nanowires be used to make carbon nanotubes?
Oh, meaning that you grow the graphene around and then you remove the silicon carbide? Is that what you were thinking about?
Yes, exactly.
That could be a good idea. I hadn't thought about that yet. It could be possible. Look, the silicon carbide is not an easy material to etch because it's very resilient. But there's a couple of wet etches that could be used. So potentially, I would have to look into that. It would be something interesting to look into. Thanks so much.
Thank you, Francesca. Sorry for my background noise.
No worries. Thanks for attending.
If anyone's got other questions, just jump in.
Francesca, very nice talk. This is Jagadish, and so really, I've got a basic question. And then, what is the origin of P-type of the graphene? And then, are they defects or impurities, or and also that can you make N-type graphene as well?
Thanks, Jagadish, for your question. Actually, let me go back here and see if I can just maybe easily go back to the slide that I need. Maybe 10. Let's see if that works. No, I can't do that here like that. Sorry, I would have to go to scroll through. Otherwise, I would have to unshare. I wanted to show you again the DFT calculations that's the easiest one for displaying in this part. And we're getting there. Almost. Yes, here. Okay, it's basically charge transfer, Jagadish. Basically, as I was explaining, intrinsically when we use this approach to graphitize silicon carbide, I didn't explain the very details, but because we have oxygen in the system, and we start basically releasing the carbon from the silicon carbide, the dangling bonds combine with an oxygen. So what happens is that we have a very, very thin layer of oxidized silicon carbide at the top of the substrate. And because this is basically exposed directly to the graphene and clearly they are in close proximity, we have charge transfer of the graphene with this oxidized system. you probably know that if we were growing that in the way, the pure decomposition of silicon carbide, in that case, actually, we would have a slightly N-type, again, because of charge transfer, because it would be a different system. But in this case, because of the oxidation, we have a P-type.
Yeah,
So
okay.
that's the reason why it's
Okay. Thank you.
Thanks, Jagdish.
Another question is that what is, I mean, of course you showed up the grain size and its impact and other things. So the most of the studies, even with using the metal as a catalyst, and most of them are polycrystalline graphene, though Rodroff and others have shown that if you use single crystalline metal, then you can be able to get single crystalline graphene. So considering that silicon carbide itself is single crystalline, what is limiting us to be able to make the epitaxial graphene, particularly when you are doing the epitaxial LPE process?
Your question is about what is limiting the grain size? Is that?
Yeah.
Okay. Well, on the epitaxial graphene on the actual silicon carbide wafers, they have already reached micron and higher. Indeed, so in some of the cases, you can see that they can also reach ballistic. So if they have a certain step on the silicon carbide, they can create a nanoribbon where they can even reach ballistic conduction. But that's a different system. So although it's defective, the silicon carbide wafer is certainly not as defective as the silicon carbide on silicon. The reason is that we have about 20% lattice mismatch between the silicon carbide and the silicon. So it's really, really hard to obtain a clean layer. You would have to grow it for really quite a thick layer before getting those defects down. So we are really, really much more constrained in that term. And this is also the reason why if you just do the thermal decomposition, just the sublimation, you never really get a consistent graphene.
Yeah.
You have to get around that.
Okay, so essentially you got already defected substrate, and that's really propagating into the graphene itself. Yeah. Okay. Good. Okay. Thank you.
That's exactly right.
Other questions from people?
But basically, as I was saying during my talk, Jagdish, the grain size, of course, is a limitation if you're talking about mobilities and such. But it's only not just the grain size, is the control of the interfaces as well. That is very important.
Yeah, sure, absolutely. Yeah.
But in terms of sheet resistance, that's not a problem.
Yeah.
And in terms of other applications, it actually could be the fact of having high charge concentration. I didn't show that on the dispersion curve, but the momentum matching between the free photon space and the curvature of the response for high charge concentration in graphene is better. It means that the momentum matching is going to be easier, potentially, with a high charge concentration in graphene. So also for those type of applications, this could be actually beneficial. So it's all a matter of understanding where we are and what you can do with it.
Yep. Very good. Thank you.
Is anyone? Oh, sorry, Jagdish, did you have another question?
Jason, I think since nobody's asking questions and I'm trying to entertain here, so then
you can be Captain Entertainer.
Thank you. So basically, it's very interesting, your brain interface studies, and it really looks very exciting as well. So you're able to really create this wireless way of really measuring the brain signals. Is that right? You're using the wireless communications essentially while designing the circuit itself?
That's right. That's right. So this is integrated in the helmet part. I probably cannot say too much because we're recording right now. Is that?
Oh, sorry. Yeah, we're still recording.
Okay, sorry. Okay, then I'll keep quiet.
Happy to follow up.
No, we'll privately talk about this. That's okay. Sorry, I apologize. Yeah.
So I'll take that one offline. If has anyone got other questions?
I have a quick question, Francesca. It's Laurie here from UWA. My impression is, if you were to grow epitaxial graphene on silicon carbide, are you saying that you would not have grain boundaries?
On silicon carbide wafers, you mean?
Yeah.
You would have much bigger grain boundaries. I think is
how much is much bigger?
orders of magnitude. So we're talking about microns instead than the 100 nanometers.
Okay.
I think the tens of microns is quite routine these days.
Okay. So we haven't reached the stage where I could say you're going to grow an epitaxial single crystal graphene on a 2-inch or 3-inch wafer.
On the carbide wafers, you mean?
Yeah.
I'm probably not the best person to respond to that because I might not necessarily know the very latest progresses, but I think tens of microns is probably what I heard. My latest information. I don't know if they went beyond that.
And sorry, I missed. How thick are your graphene films?
Our graphene films are typically a few layers, so 3 to 4 layers typically. Okay. We can grow it thicker as well, but let's say we can usually typically what we're talking about is 2 to 4 layers.
No. At some stage, maybe later on, we should also talk about maybe some work together on transport properties, because using our capabilities.
Absolutely.
Yeah.
Thanks, Laurie. All right.
And sorry, I have to go. I've got another meeting at 10 in 1 minute.
I think we got to noon anyway, so.
Got right to noon. Has anyone got questions though, before Francesca signs off?
And of course, if there's any questions, feel free to email me.
Yeah. Okay then, Francesca, thank you very much for that talk. I'm sure it was enlightening for everyone, and there was a couple on Twitter who were asking whether it was going to be recorded. So now that we know that it is, they'll be very happy. But yeah, thank you very much, Francesca. Enjoy the rest of the week.
Thanks, everyone.
Thanks, Francesca. Great talk. And thanks, Jason, for organizing it.
Bye.
Bye all.